Hi everyone. In this video we're going to talk a little bit about how to use integrals to compute volumes of different solids. The beginning of the video is going to be a little bit of a review of what we saw in the Zoom meeting. I'll go through those examples again so you have that for as reference. And then I'll cover a couple more examples with some more complicated cases. But let's get started. So to remind you, in the beginning we talked about the volume of some simple regions. So we discussed the case of, for example, a cylinder. Let me try to draw a cylinder. It's supposed to be very regular, but it's hard to draw it very symmetric. But it's the same. It's just a circle translated up and down. Oh, it's gonna trip me up. All right. So a cylinder has two important numbers to understand its dimensions. So there's the radius of the circle, which is the base of the cylinder. You can draw it in the top or in the bottom. There's another circle down here. And there's the height of the cylinder. So this is a right cylinder. It's a right cylinder because the angle of the cross section with the height is 90 degrees, right? So and in this case, the volume you can compute by using the area of the base of the cylinder. So the area of the base is a circle. So the area of a circle is pi times the radius squared. Right? So pi r squared times the height of the cylinder. Right? So here's h. Forgot to write that. So base, the area of the base times the height of the cylinder, right? Another example, which is pretty simple that we discussed, is a box, a rectangular box. Hopefully I'm not going to mess this up too much. So if you draw a box like this, the important dimensions here are, well, there's the length of the base rectangle, the width of the base rectangle, and then the height of the box. But again, the volume can be computed, well, it's just a multiplication of these three numbers, but you can think of it as area of the base, which is now a rectangle, so L times W, right? That's the area of the rectangle, length times width, times the height of the box, right? But the problem is, what happens with these pictures is that if you intersect this picture here with a horizontal plane perpendicular, right, you always get the same picture, right? So in the cylinder, you're always going to get a circle of radius r. And on the box, if you intersect with a horizontal plane, and you look at this cross section, you always get a rectangle with the same dimensions, L and H, L and W, sorry. But what happens with more complicated solids where maybe the cross sections are changing, right? So for more complicated solids, more complicated regions, let me want the purple. Volumes. All right. So you can draw it here. Let me draw an x-axis. And then I'll just draw some random region here. Some pottery of some sort. Okay, so you have a region like this. And the thing with this region is, as you see, if we start slicing this region using planes that are perpendicular to the x-axis and look at this cross section, you see a certain cross section here. Right? Well, the thing is that this cross section now is changing, right? It's changing as you change the x, right? The variable x. So this is what we're going to call a cross section of the region. And what we must do here to try to compute this volume is try to compute how does the area of this cross section change as we change our choice of the variable x, right? So for different values of x, the area of this cross section is going to be different. And but so what we're going to do, let me call the smallest value of x a and the biggest value of x b, right? So for x ranging from a to b, we let ax be the area of the cross section at x. Well, so what is the idea to compute this volume? I'm gonna draw something. So basically, you can think of this cross section, maybe thicken it up just a little bit and draw a little very short cylinder. Let me see if I can do this. It's pretty difficult, but right. So, but you can imagine a very you thicken it a little bit, so it's like a very short cylinder. The volume of the cylinder would be the, again, area of the base times height, right? So if this is very short and this area here is delta x, say, right, very small, then you can approximate the volume of the solid by, you sum, you chop it up into a bunch of stuff and you sum from 1 all the way to n. The volumes of these cylinders, the volumes are base. So say that this is xi, right? The one of the sample points times height, right? This is the volume of the tiny cylinder. You add all of them up, and then you send delta x to 0, which is the same as sending the number of samples that you take to infinity. But in the end, the formula that you see is the formula that we saw in class, is that the volume V is going to be equal to the integral from a to b, these two bounds, of ax dx, right? That's the integral formula for the volume of a solid like this, right? So you want to think of this formula as, for every value of x, you compute the cross section. You see the area of that cross section, a of x, and then this is like the volume of an infinitesimally thick cylinder, right? And you add all of them, all of these cross sections from a to b. That's what this integral symbol is doing, right? Well, so let me go through the example of the sphere again, so we see how to use this this formula. Example, volume of the sphere of radius r. Okay, so let's first draw a picture of the sphere. So x-axis, the y-axis. So as I said, usually this is x, y, z when you're in 3 dimensions, but for this type of problem, we're going to call this x and this y, and we're going to just leave this axis nameless. But so let me try to draw a sphere here. Okay, not super round, but okay, so this is a sphere, and the radius of the sphere is r, right? So this is r, this length. So one thing that we can see here is, all right, we're going to try to compute this volume by fixing our variable r and then analyzing the cross sections, right? Well, but one thing that we can already figure out, so perhaps I can fix an x already. So let me erase this r here because it's going to get too many things in the. Let me use the purple here. So if we fix a value here of the coordinate x, we can look at the cross section through that, right? So you take a plane. Oops. You take a plane perpendicular to. Let me deactivate my notifications here. Yeah, so you take a plane perpendicular to the x-axis and you intersect with your sphere and with your ball, and you see this cross section. And we just need to compute a formula for the area of this cross section, a of x. And then we have to integrate from the smallest to the biggest value of the variable x inside of our region. The biggest value, as you see, this is at the end of the radius of the sphere. It has to be r. Right? That's the biggest value of the variable x, and the smallest value is negative r. So the volume v is going to be the integral from negative r to r of the area of the cross section dx. Right, so this is like the infinitesimal volume of one of these cylinders. All right, so negative r to r, we're good. We just need to figure out what is this area, right? So when you intersect the sphere with a vertical plane, this picture that you see here is actually exactly a circle, right? It's a circle, a vertical circle, and we just need to compute the area of a circle. The area of a circle depends on the radius of this circle. So as long as we compute this radius, so let me draw here, you see in green this line from the center of the circle to the boundary. As long as we compute this length, then we know the radius of the circle, and so we can write the area of the circle, right? Okay, so I'm going to draw another picture here because we're going to have to figure out a formula for that radius, right? So if this is our sphere, I'm drawing now in 2 dimensions, x, y. So this, it doesn't look great, but it's okay for our purpose. If this is r, and this is the cross section that we fixed. Okay, so I'm just ignoring this axis here. I'm just drawing everything in 2 dimensions. What we want to figure out is what is this length here. Right? This is the radius of the circle, right there. How to figure out that length? Well, we know that this length here is x, right? Is whatever value that we fixed for x in the variable x. And we know that this length here, you see that there's a little triangle that this forms. So this length we also know because it connects the center of the sphere to the sphere. It has to be the radius, right? If I draw over here, right, it connects the center of the sphere to the sphere. So it's a radius of the sphere. So it has to be r, the radius of our sphere. Yeah? And so with this, we can use, this is a right triangle. We can use the Pythagorean theorem, right? It says that the two sides of the triangle squared, so x squared plus r of x squared, has to be equal to the hypotenuse squared. And so this gives us a formula for this little r, the radius that we're looking for. R of x squared is equal to uppercase r squared minus x squared. If you want, then this radius is the square root of this, right? That's the radius of that circle, right? And the area then, the area of the cross section is pi times this radius squared, which is pi, well, you square out the square root, right? And you get r squared minus x squared. That's the formula for the cross section. Okay, And once we have this, then we're good to go here on this integral. This is the integral from negative r to r. The area of the cross section we computed is pi times r squared minus x squared dx. Okay. And as I said, you can use a little trick here to make your life a little bit easier. Because this function that you're integrating is an even function, you could do 2 times the integral from 0 to r. But since I did that in class, now I'm going to, well, I'll do it without that trick. So if you do that, then the antiderivative pi r squared, that's just a number, right? Pi r squared. The antiderivative of a number is the number times the variable x. Right? So pi r squared x. And here you get negative pi r squared, negative pi x squared, I'm sorry. Negative pi x squared, the antiderivative is negative pi x cubed over 3. And you need to plug in x equals r and x equals negative r. If you do that, then plugging in r, you get pi r squared times r minus pi r cubed over 3 minus, now you plug in negative r, so pi r squared times negative r minus pi negative r cubed over 3. Okay, so this is pi r cubed minus pi r cubed over 3. You're going to get 2 pi r cubed over 3. And here, this becomes a negative term. The negative sign comes out in the front. But this becomes a positive term because a negative r cubed is negative r quantity cubed. Okay? And then these two negatives turn into a positive. So this turns negative, this turns positive. But then there's a negative sign outside. So this is positive and this is negative after you multiply the negative sign. And it turns exactly equal to this, right? So it's plus 2 pi r cubed. This is exactly the same thing. So we get 4 pi r cubed over 3. Okay? So the volume of the sphere of radius r is 4 pi r cubed over 3, right? Units of volume, whatever they are, right? So if our axes are in units of meter, then that would be 4 pi r cubed over 3 meters cubed. But if the axes are measured in inches, then that would be inches cubed, right? So whatever units of volume. We're not paying too much attention right now to the units of the problem. Okay, let's do one more example. I think I'll start in a fresh page. So that's the example where we rotate a certain area. Example 2. Find the volume obtained volume of the region obtained by rotating the area under the graph y equals square root of x from x equals 0 to x equals 1 about the x-axis. Find the volume of the region obtained by rotating the area under the graph y equals root x from x0 to x1 about the x-axis. Okay, so in this problem, let's draw what's happening. So you have here the y-axis and the x-axis. And y equals root x, you can think of it, if you square both sides, as x equals y squared. It's a parabola, but it goes sideways like this. So that's y equals root x. And we're only considering it from x equals 0 to x equals 1. So the area under the graph is going to be this bit. Now we're going to take the area under the graph y equals root x from x0 to x1, and we're going to rotate it about the x-axis. So we're going to get a solid region that looks like, I don't want blue. It looks like this. That's ugly. All right. So we're trying to compute the volume of this solid now, right? Where this is 1, yeah. Okay, and to compute the volume, it's a similar strategy. You just slice it into vertical cross sections, right? So you fix a value of x and you see the vertical cross section through that point in the x-axis, and you try to compute a formula for ax, right? And so the volume V of this region, we see it's going to be an integral. The smallest value of the x variable in your region is x equals 0 right here at the origin. And the biggest value of the biggest value of the variable x is x equals 1 right here at the top. Okay? So you integrate from 0 to 1 the area of this cross section dx. So as long as we find a formula here, we can compute this volume. But again, we rotated this graph around the x-axis, right? So this purple, it doesn't look super great in this drawing, but this purple region here is actually a circle, right? So this boundary here is a circle. We rotated the graph around the x-axis. So as long, again, as we find the radius of the circle, we are able to compute the area of the circle, right? How do we compute this radius? Well, pay attention at this point right at the top here, because the radius of this circle is the y-coordinate of this point, right? The y-coordinate of this point is the radius of the circle. And how can we figure out what the y-coordinate of this point is? Well, first, we know the x-coordinate. This is the cross-section at x, so x is given to us. Maybe I'll draw it in green. I don't know if this is a little too messy, but x. Right? The x-coordinate is x. The y-coordinate, well, this point is on the graph y equals root x, right? So the y-coordinate is root x. So if this length here is little r of x, then the radius of that circle is root x, and the area is just pi radius squared, which is pi root x squared, which is x, right? So that's the formula for the area of the cross section. And now we can integrate. This is the integral from 0 to 1. The area of the cross section is pi x dx. Antiderivative is easy here. It's pi x squared over 2. Plug in x equals 1 and x equals 0. If you plug in x equals 1, you get pi over 2. Plug in x equals 0, you get 0. Pi times 0 is 0. And that's it. The volume of the region is pi over 2 units of volume. All right, well, let's do now an example that we did not see in the Zoom meeting earlier today. So, and this is an example where we're going to get an integral in the y variable. Okay, that can happen as well with volumes. So, example 3. All right, so let r, well, r looks like a radius, right? But maybe I'll do a scripty looking r, be the region. There's a plane or something outside. Bounded by the curves y equals x cubed, y equals 8, and x equals 0. The region, I should say, in the plane. Excuse me. Find the volume of the, I'm going to call it solid, obtained by rotating this region, script r, about the y-axis. Okay, so now we're rotating around a different axis. It's going to be a little bit different. Ooh, I need a new page. Okay. I want to have the statement of the problem at the same time, so I'll try to draw it right here. Okay, so first, let's draw the region R, and then we're going to rotate it. So here's the y-axis and the x-axis. So first, y equals x cubed. This is a cubic, right? Hopefully you remember how the graph looks. To the right, it kind of looks like a parabola, a little steeper, but our drawing is definitely not exact enough so you can tell. And then on the other side, it goes down, right? That's why y equals x cubed. All right, that's one curve. Y equals 8. This is the set of all points that have exactly the same y coordinate. Y coordinate equals to 8. This gives you a horizontal line. Okay. All of these points have exactly the same y coordinate. Their x coordinate can be anything, but their y coordinate has to be 8. Right? So it gives you that. Maybe let me do it in green. Okay, so this is green. Not parabola, the cubic, I just drew it in black. Okay. Now this is green, and then x equals 0. This is also going to be a line of all the points that have x coordinate equal to 0. All the points with x coordinate equal to 0 will actually give you the y-axis, right? All the points in the y-axis, they can have any y coordinate, but their x coordinate is always 0. So you get this line. Okay. No. Okay. So the region R is this region right here, right? Between all these curves. We're going to take this region R and we're going to rotate it about the y-axis. And we're going to get something that looks like this, right? Almost like an antenna or something. Right? That's what we want to figure out. What is the volume of this region? Now, If you try to slice it with vertical planes, that's fine, you know, it's not that big a deal. But it's not as symmetric as, or yeah, I think that's the correct word, or as pretty as slicing it with horizontal planes, right? Because of the way that this region is, I don't know, configured. Horizontal planes make the slices a lot nicer, right? So, for example, if you, I'll draw, maybe let me draw over here, down here. So, what I'm trying to say is, if you decide to slice this with vertical planes, the slices will look like this, right? Something like that. Right. And that's fine. You can try to compute the area of these slices. In the bottom, you get some sort of cubic or parabola thing, but you know it's a little bit more complicated than if instead we uh, just look at our region like that, and then we slice with horizontal planes, because you're going to get a circle again, right? Just circles if you slice it with horizontal planes. So sometimes you have to look at the problem. You know, it's pretty, although this is saying, oh, we're rotating about the y-axis, is a good giveaway that you're going to have to slice with horizontal planes. But sometimes you have to make a decision, like how are you going to slice it? But for this problem, let's see how we can do this by slicing with horizontal planes. So let's do this. All right. So it's very similar process. First, we need to compute the smallest and biggest value of the y-coordinate in our region. It's pretty clear that the biggest value is y equals 8. That's this line that we chose. And the smallest value is here when y is equal to 0. Right? So our volume integral, is going to be equal to an integral from 0 to 8. Okay? And then if you fix a value of y, you can do a horizontal slice. What color to use here? I'm running out of colors. I'll use pink. Okay. It's almost the same as purple, huh? But you slice your region with the horizontal plane at that given y coordinate, and you compute the area of that cross section, a of y now, right? Because it depends on what y coordinate you fixed. Every y coordinate will give you a different cross section. You want the area of that cross section. The volume is going to be the integral of a of y dy. Oh, I wrote it. Right? So you can think of ay dy as an infinitesimal volume of a very, very short cylinder, right? And you add all of them from 0 to 8, you get the volume of your region. Right? Okay, so it's a pretty similar process. All we have to do now is figure out a formula for a of y, and we can integrate and compute the volume. So, okay, so we need to figure out now the area of this region. We got this region by rotating the point in the graph around the y-axis, so this region is a circle. And as long as we figure out this length here, ooh, I don't know if you can see it. Maybe I'll draw it in red. All right, if we figure out this length, the radius of the circle, then we can find the formula for the area. Okay? So how to figure out this length? This is a little twisted, but it's supposed to be horizontal. Okay, that looks better. Okay, how to figure out this length? Well, why not look at this point right here? Yeah. This length is the x-coordinate of this point, right? And we know the y-coordinate of this point because it's given. That's the cross-section that we get by fixing this value of y. Now take this y, look at this point, and figure out what the x-coordinate is going to be. The x-coordinate is exactly the radius of this circle, right? How to figure out what the x-coordinate is? Well, this point is on this curve, right? Which satisfies y equals x cubed, right? So this point if the y coordinate is y, the x coordinate, you take a cube root here, right? So cube root of y is equal to x. That's the x coordinate. Oh, I barely have space. I hope this is not too messy. Cube root of y, comma y, is this point right here. Right, so that's it. That's the radius of the circle, right? So the radius r of y of the cross section is cube root of y. The area of that cross section, that's a circle, so it's pi times the radius squared. So it's going to be, this is y to the 1/3. This is going to be y to the 2/3. Right? You squared that. But that's it. Now you can now we can solve this integral. This is the integral from 0 to 8. A of y is pi y to the 2/3 dy. Okay, antiderivative is pretty easy. It's a power rule. So this is going to be pi. If you add 1 here, you get y to the 5/3. And you're going to have to divide by 5/3, which is multiplying by 3/5. Plug in y equals 0. Y equals 8 and y equals 0. Plug in y equals 8, you get 3 pi 8 to the 5 over 3 over 5. Minus plugging in 0, you get 0, right? So I'm not going to write it. And what is this? Well, you can first take this cube root, right? This is 8 to the 5/3. You can kind of write it in steps. It's 8 to the 1/3 to the 5th, right? But 8 to the 1/3, cube root of 8 is 2, right? So this is 3 pi times 2 to the 5th over 5. 2 to the 5th is, so 2 to the 4th is 4 squared, which is 16. And 2 to the 5th is 2 times that, which is 32. 3 times 32 is 96 pi over 5. That's it. So the volume of the region is 96 pi over 5. All right. Well, there are 2 more examples that I want to show you. Perhaps I'll put them in a separate video. Okay, so I think I'll finish this video here. I'll make it part 1. And on the next video, I'll give you a couple more examples where all of the slices that we have seen are circles. So I'll give you 2 examples where the slices are going to be annuli. So it's going to be an annulus. It's also called a washer. Yeah, I'll see you in the next video with those examples.